Hi and welcome to another video. Today we are going to understand the basics of machine learning. I have lecture slides, and those who want to download the code, please check the article in the description. I have put proper explanation for each line code. You can download it and just play with the code till you understand it. When most people hear machine learning, they picture a robot, a dependable butler, or a deadly terminator, depending on whom you ask. But machine learning is not just a futuristic fantasy, it's already here. In fact, it has been around for decades in some specialized applications, such as optical character recognition, OCR. But the first ML application that really became mainstream, improving the lives of hundreds of millions of people, took over the world back in the 1990s, the spam filter. It's not exactly a self-aware Skynet, but it does technically qualify as machine learning. It has actually learned so well that you seldom need to flag an email as spam anymore. It was followed by hundreds of ML applications that now quietly power hundreds of products and features that you use regularly, from better recommendations to voice search. Where does machine learning start and where does it end? What exactly does it mean for a machine to learn something? If I download a copy of Wikipedia, has my computer really learned something? Is it suddenly smarter? In this chapter, we will start by clarifying what machine learning is and why you may want to use it. Then, before we set out to explore the machine learning continent, we will take a look at the map and learn about the main regions and the most notable landmarks: supervised versus unsupervised learning, online versus batch learning, instance-based versus model-based learning. Then we will look at the workflow of a typical ML project, discuss the main challenges you may face, and cover how to evaluate and fine-tune a machine learning system. This chapter introduces a lot of fundamental concepts and jargon that every data scientist should know by heart. It will be a high-level overview. It's the only chapter without much code, all rather simple, but you should make sure everything is crystal clear to you before continuing on to the rest of the book. So grab a coffee and let's get started. What is machine learning? Machine learning is the science and art of programming computers so they can learn from data. Here is a slightly more general definition. Machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. Arthur Samuel, 1959. In a more engineering-oriented one, a computer program is said to learn from experience E with respect to some task T and some performance measure P, if its performance on T, as measured by P, improves with experience E. Tom Mitchell, 1997. Your spam filter is a machine learning program that, given examples of spam emails, example, flagged by users, and examples of regular, non-spam, also called ham, emails, can learn to flag spam. The examples that the system uses to learn are called the training set. Each training example is called a training instance or sample. In this case, the task T is to flag spam for new emails, the experience E is the training data, and the performance measure P needs to be defined. For example, you can use the ratio of correctly classified emails. This particular performance measure is called accuracy, and it is often used in classification tasks. If you just download a copy of Wikipedia, your computer has a lot more data, but it is not suddenly better at any task. Thus, downloading a copy of Wikipedia is not machine learning. Why use machine learning? Consider how you would write a spam filter using traditional programming techniques. Figure 1:1. First, you would consider what spam typically looks like. You might notice that some words or phrases, such as for you, credit card, free, and amazing, tend to come up a lot in the subject line. Perhaps you would also notice a few other patterns in the sender's name, the email's body, and other parts of the email. You would write a detection algorithm for each of the patterns that you noticed, and your program would flag emails as spam if a number of these patterns were detected. You would test your program and repeat steps 1 and 2 until it was good enough to launch. MLS 20101 Figure 1:1. The traditional approach, since the problem is difficult, your program will likely become a long list of complex rules, pretty hard to maintain. In contrast, a spam filter based on machine learning techniques automatically learns which words and phrases are good predictors of spam by detecting unusually frequent patterns of words in the spam examples compared to the ham examples, figure 1:2. The program is much shorter, easier to maintain, and most likely more accurate. What if spammers notice that all their emails containing "for you" are blocked? They might start writing "for you" instead. A spam filter using traditional programming techniques would need to be updated to flag "for you" emails. If spammers keep working around your spam filter, you will need to keep writing new rules forever. In contrast, a spam filter based on machine learning techniques automatically notices that "for you" has become unusually frequent in spam flagged by users, and it starts flagging them without your intervention, figure 1 to 3. Another area where machine learning shines is for problems that either are too complex for traditional approaches or have no known algorithm. For example, consider speech recognition. Say you want to start simple and write a program capable of distinguishing the words "one" and "two." You might notice that the word "two" starts with a high-pitched sound, T, so you could hard-code an algorithm that measures high-pitched sound intensity and use that to distinguish ones and twos. But obviously this technique will not scale to thousands of words spoken by millions of very different people in noisy environments and in dozens of languages. The best solution, at least today, is to write an algorithm that learns by itself, given many example recordings for each word. Finally, machine learning can help humans learn, figure 1 to 4. ML algorithms can be inspected to see what they have learned, although for some algorithms this can be tricky. For instance, once a spam filter has been trained on enough spam, it can easily be inspected to reveal the list of words and combinations of words that it believes are the best predictors of spam. Sometimes this will reveal unsuspected correlations or new trends, and thereby lead to a better understanding of the problem. Applying ML techniques to dig into large amounts of data can help discover patterns that were not immediately apparent. This is called data mining. To summarize, machine learning is great for problems for which existing solutions require a lot of fine-tuning or long lists of rules. One machine learning algorithm can often simplify code and perform better than the traditional approach. Complex problems for which using a traditional approach yields no good solution, the best machine learning techniques can perhaps find a solution. Fluctuating environments, a machine learning system can adapt to new data. Getting insights about complex problems and large amounts of data. Detecting tumors in brain scans. This is semantic segmentation, where each pixel in the image is classified, as we want to determine the exact location and shape of tumors, typically using CNNs as well. Types of machine learning systems. There are so many different types of machine learning systems that it is useful to classify them in broad categories, based on the following criteria: whether or not they are trained with human supervision, supervised, unsupervised, semi-supervised, and reinforcement learning, whether or not they can learn incrementally on the fly, online versus batch learning, whether they work by simply comparing new data points to known data points, or instead by detecting patterns in the training data and building a predictive model, much like scientists do. Instance-based versus model-based learning. These criteria are not exclusive, you can combine them in any way you like. For example, a state-of-the-art spam filter may learn on the fly using a deep neural network model trained using examples of spam and ham. This makes it an online, model-based, supervised learning system. Let's look at each of these criteria a bit more closely. Supervised/unsupervised learning. Machine learning systems can be classified according to the amount and type of supervision they get during training. There are 4 major categories: supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. Supervised learning. In supervised learning, the training set you feed to the algorithm includes the desired solutions, called labels. A typical supervised learning task is classification. The spam filter is a good example of this. It is trained with many example emails along with their class, spam or ham, and it must learn how to classify new emails. Another typical task is to predict a target numeric value, such as the price of a car, given a set of features, mileage, age, brand, etc., called predictors. This sort of task is called regression. Figure 1 to 6. Point 1. To train the system, you need to give it many examples of cars, including both their predictors and their labels, i.e., their prices. Unsupervised learning. In unsupervised learning, as you might guess, the training data is unlabeled. The system tries to learn without a teacher. Here are some of the most important unsupervised learning algorithms. Clustering. K-means discan hierarchical cluster analysis, HCA. anomaly detection and novelty detection. 1 class SVM isolation forest visualization and dimensionality reduction principal component analysis, PCA, kernel PCA locally linear embedding, LLT distributed stochastic neighbor embedding, TSN, association rule learning a priori eclat. For example, say you have a lot of data about your blog's visitors. You may want to run a clustering algorithm to try to detect groups of similar visitors, figure 1 to 8. At no point do you tell the algorithm which group a visitor belongs to, it finds those connections without your help. For example, it might notice that 40% of your visitors are males who love comic books and generally read your blog in the evening, while 20% are young sci-fi lovers who visit during the weekends. If you use a hierarchical clustering algorithm, it may also subdivide each group into smaller groups. This may help you target your posts for each group. Visualization algorithms are also good examples of unsupervised learning algorithms. You feed them a lot of complex and unlabeled data, and they output a 2D or 3D representation of your data that can easily be plotted, figure 1 to 9. These algorithms try to preserve as much structure as they can, example, trying to keep separate clusters in the input space from overlapping in the visualization, so that you can understand how the data is organized and perhaps identify unsuspected patterns. It is often a good idea to try to reduce the dimension of your training data using a dimensionality reduction algorithm before you feed it to another machine learning algorithm, such as a supervised learning algorithm. It will run much faster, the data will take up less disk and memory space, and in some cases it may also perform better. Yet another important unsupervised task is anomaly detection, for example, detecting unusual credit card transactions to prevent fraud, catching manufacturing defects, or automatically removing outliers from a dataset before feeding it to another learning algorithm. The system is shown mostly normal instances during training, so it learns to recognize them. Then, when it sees a new instance, it can tell whether it looks like a normal one or whether it is likely an anomaly, see figure 1 to 10. A very similar task is novelty detection. It aims to detect new instances that look different from all instances in the training set. This requires having a very clean training set, devoid of any instance that you would like the algorithm to detect. For example, if you have thousands of pictures of dogs, and 1% of these pictures represent chihuahuas, then a novelty detection algorithm should not treat new pictures of chihuahuas as novelties. On the other hand, anomaly detection algorithms may consider these dogs as so rare and so different from other dogs that they would likely classify them as anomalies, no offense to chihuahuas. Finally, another common unsupervised task is association rule learning, in which the goal is to dig into large amounts of data and discover interesting relations between attributes. For example, suppose you own a supermarket. Running an association rule on your sales logs may reveal that people who purchase barbecue sauce and potato chips also tend to buy steak. Thus, you may want to place these items close to one another. Semi-supervised learning. Since labeling data is usually time-consuming and costly, you will often have plenty of unlabeled instances and few labeled instances. Some algorithms can deal with data that's partially labeled. This is called semi-supervised learning, figure 1 to 11. MLS 20111 figure 1 to 11. Semi-supervised learning with two classes, triangles and squares. The unlabeled examples, circles, help classify a new instance, the cross, into the triangle class rather than the square class, even though it is closer to the labeled squares. Some photo hosting services, such as Google Photos, are good examples of this. Once you upload all your family photos to the service, it automatically recognizes that the same person A shows up in photos 1, 5, and 11, while another person B shows up in photos 2, 5, and 7. This is the unsupervised part of the algorithm, clustering. Now all the system needs is for you to tell it who these people are. Just add one label per person 4 and it is able to name everyone in every photo, which is useful for searching photos. Most semi-supervised learning algorithms are combinations of unsupervised and supervised algorithms. For example, deep belief networks, DBNs, are based on unsupervised components called restricted Boltzmann machines, RBMs, stacked on top of one another. RBMs are trained sequentially in an unsupervised manner, and then the whole system is fine-tuned using supervised learning techniques. Reinforcement learning is a very different beast. The learning system, called an agent in this context, can observe the environment, select and perform actions, and get rewards in return. It must then learn by itself what is the best strategy, called a policy, to get the most reward over time. A policy defines what action the agent should choose when it is in a given situation. For example, many robots implement reinforcement learning algorithms to learn how to walk. DeepMind's AlphaGo program is also a good example of reinforcement learning. It made the headlines in May 2017 when it beat the world champion Ku Jia at the game of Go. It learned its winning policy by analyzing millions of games, and then playing many games against itself. Note that learning was turned off during the games against the champion. AlphaGo was just applying the policy it had learned. Batch and online learning. Another criterion used to classify machine learning systems is whether or not the system can learn incrementally from a stream of incoming data. In batch learning, the system is incapable of learning incrementally. It must be trained using all the available data. This will generally take a lot of time and computing resources, so it is typically done offline. First the system is trained, and then it is launched into production and runs without learning anymore. It just applies what it has learned. This is called offline learning. If you want a batch learning system to know about new data, such as a new type of spam, you need to train a new version of the system from scratch on the full dataset, then stop the old system and replace it with the new one. Fortunately, the whole process of training, evaluating, and launching a machine learning system can be automated fairly easily, so even a batch learning system can adapt to change. Simply update the data and train a new version of the system from scratch as often as needed. This solution is simple and often works fine, but training using the full set of data can take many hours, so you would typically train a new system only every 24 hours or even just weekly. If your system needs to adapt to rapidly changing data, then you need a more reactive solution. In online learning, you train the system incrementally by feeding it data instances sequentially, either individually or in small groups called mini-batches. Each learning step is fast and cheap, so the system can learn about new data on the fly, as it arrives. In online learning, a model is trained and launched into production, and then it keeps learning as new data comes in. Online learning is great for systems that receive data as a continuous flow, example stock prices, and need to adapt to change rapidly or autonomously. It is also a good option if you have limited computing resources. Once an online learning system has learned about new data instances, it does not need them anymore, so you can discard them. This can save a huge amount of space. Online learning algorithms can also be used to train systems on huge datasets that cannot fit in one machine's main memory. This is called out-of-core learning. The algorithm loads part of the data, runs a training step on that data, and repeats the process until it has run on all of the data. Out-of-core learning is usually done offline, not on the live system, so online learning can be a confusing name. Think of it as incremental learning. One important parameter of online learning systems is how fast they should adapt to changing data. This is called the learning rate. If you set a high learning rate, then your system will rapidly adapt to new data, but it will also tend to quickly forget the old data. Conversely, if you set a low learning rate, the system will have more inertia, that is, it will learn more slowly, but it will also be less sensitive to noise in the new data or to sequences of non-representative data points, outliers. A big challenge with online learning is that if bad data is fed to the system's performance will gradually decline. If it's a live system, your clients will notice. For example, bad data could come from a malfunctioning sensor on a robot, or from someone spamming a search engine to try to rank high in search results. To reduce this risk, you need to monitor your system closely and promptly switch learning off, and possibly revert to a previously working state if you detect a drop in performance. You may also want to monitor the input data and react to abnormal data, example, using an anomaly detection algorithm. Instance-based versus model-based learning. One more way to categorize machine learning systems is by how they generalize. Most machine learning tasks are about making predictions. This means that given a number of training examples, the system needs to be able to make good predictions for, generalize to, examples it has never seen before. Having a good performance measure on the training data is good, but insufficient. The true goal is to perform well on new instances. There are two main approaches to generalization: Instance-based learning and model-based learning. Instance-based learning, possibly the most trivial form of learning, is simply to learn by heart. If you were to create a spam filter this way, it would just flag all emails that are identical to emails that have already been flagged by users. Not the worst solution, but certainly not the best. Instead of just flagging emails that are identical to known spam emails, your spam filter could be programmed to also flag emails that are very similar to known spam emails. This requires a measure of similarity between two emails. A very basic similarity measure between two emails could be to count the number of words they have in common. The system would flag an email as spam if it has many words in common with a known spam email. This is called instance-based learning. The system learns the examples by heart, then generalizes to new cases by using a similarity measure to compare them to the learned examples, or a subset of them. For example, in Figure 1 to 15 the new instance would be classified as a triangle because the majority of the most similar instances belong to that class. Model-based learning. Another way to generalize from a set of examples is to build a model of these examples and then use that model to make predictions. This is called model-based learning, Figure 1 to 16. For example, suppose you want to know if money makes people happy, so you download the Better Life Index data from the OECD's website and stats about gross domestic product, GDP, per capita from the IMF's website. Then you join the tables and sort by GDP per capita. There does seem to be a trend here. Although the data is noisy, i.e., partly random, it looks like life satisfaction goes up more or less linearly as the country's GDP per capita increases. So you decide to model life satisfaction as a linear function of GDP per capita. This step is called model selection. You selected a linear model of life satisfaction with just one attribute, GDP per capita. This model has two model parameters, θ0 and θ1.5. By tweaking these parameters, you can make your model represent any linear function. Before you can use your model, you need to define the parameter values θ0 and θ1. How can you know which values will make your model perform best? To answer this question, you need to specify a performance measure. You can either define a utility function or fitness function that measures how good your model is, or you can define a cost function that measures how bad it is. For linear regression problems, people typically use a cost function that measures the distance between the linear model's predictions and the training examples. The objective is to minimize this distance. This is where the linear regression algorithm comes in. You feed it your training examples, and it finds the parameters that make the linear model fit best to your data. This is called training the model. In our case, the algorithm finds that the optimal parameter values are θ0 equals 4.85 and θ1 equals 4.91 times 10 to 5. You are finally ready to run the model to make predictions. For example, say you want to know how happy Cypriots are, and the OECD data does not have the answer. Fortunately, you can use your model to make a good prediction. You look up Cyprus's GDP per capita, find $22,587, and then apply your model and find that life satisfaction is likely to be somewhere around 4.85 plus 22,587 times 4.91 times 10 minus 5 is equal to 5.96. To whet your appetite, example 1-to-1 shows the Python code that loads the data, prepares it, 6 creates a scatterplot for visualization, and then trains a linear model and makes a prediction. Example 1-to-1. Training and running a linear model using scikit-learn. I won't discuss the code here, as this is self-explanatory. You can check the link in description to find this code and a written explanation along with it. Main challenges of machine learning. In short, since your main task is to select a learning algorithm and train it on some data, the two things that can go wrong are bad algorithm and bad data. Let's start with examples of bad data. Insufficient quantity of training data for a toddler to learn what an apple is. All it takes is for you to point to an apple and say, "Apple," possibly repeating this procedure a few times. Now the child is able to recognize apples in all sorts of colors and shapes. Genius! Machine learning is not quite there yet. It takes a lot of data for most machine learning algorithms to work properly. Even for very simple problems you typically need thousands of examples, and for complex problems such as image or speech recognition you may need millions of examples, unless you can reuse parts of an existing model. Non-representative training data. In order to generalize well, it is crucial that your training data be representative of the new cases you want to generalize to. This is true whether you use instance-based learning or model-based learning. For example, the set of countries we used earlier for training the linear model was not perfectly representative. A few countries were missing. Figure 1 to 21 shows what the data looks like when you add the missing countries. If you train a linear model on this data, you get the solid line, while the old model is represented by the dotted line. As you can see, not only does adding a few missing countries significantly alter the model, but it makes it clear that such a simple linear model is probably never going to work well. It seems that very rich countries are not happier than moderately rich countries. In fact, they seem unhappier, and conversely some poor countries seem happier than many rich countries. By using a non-representative training set, we trained a model that is unlikely to make accurate predictions, especially for very poor and very rich countries. It is crucial to use a training set that is representative of the cases you want to generalize to. This is often harder than it sounds. If the sample is too small, you will have sampling noise, i.e., non-representative data as a result of chance, but even very large samples can be non-representative if the sampling method is flawed. This is called sampling bias. Poor quality data. Obviously, if your training data is full of errors, outliers, and noise, example, due to poor quality measurements, it will make it harder for the system to detect the underlying patterns, so your system is less likely to perform well. It is often well worth the effort to spend time cleaning up your training data. The truth is, most data scientists spend a significant part of their time doing just that. The following are a couple of examples of when you'd want to clean up training data. If some instances are clearly outliers, it may help to simply discard them or try to fix the errors manually. As the saying goes, garbage in, garbage out. Your system will only be capable of learning if the training data contains enough relevant features and not too many irrelevant ones. A critical part of the success of a machine learning project is coming up with a good set of features to train on. This process, called feature engineering, involves the following steps: feature selection, selecting the most useful features to train on among existing features; feature extraction, combining existing features to produce a more useful one. As we saw earlier, dimensionality reduction algorithms can help, creating new features by gathering new data. As you might guess, underfitting is the opposite of overfitting. It occurs when your model is too simple to learn the underlying structure of the data. For example, a linear model of life satisfaction is prone to underfit. Reality is just more complex than the model, so its predictions are bound to be inaccurate, even on the training examples. Here are the main options for fixing this problem. Select a more powerful model, with more parameters. Feed better features to the learning algorithm, feature engineering. Reduce the constraints on the model, example, reduce the regularization hyperparameter. Machine learning is about making machines get better at some task by learning from data, instead of having to explicitly code rules. There are many different types of ML systems, supervised or not, batch or online, instance-based or model-based. In an ML project, you gather data in a training set, and you feed the training set to a learning algorithm. If the algorithm is model-based, it tunes some parameters to fit the model to the training set, i.e., to make good predictions on the training set itself, and then hopefully it will be able to make good predictions on new cases as well. If the algorithm is instance-based, it just learns the examples by heart and generalizes to new instances by using a similarity measure to compare them to the learned instances. The system will not perform well if your training set is too small, or if the data is not representative, is noisy, or is polluted with irrelevant features. Garbage in, garbage out. Lastly, your model needs to be neither too simple, in which case it will underfit, nor too complex, in which case it will overfit. The only way to know how well a model will generalize to new cases is to actually try it out on new cases. One way to do that is to put your model in production and monitor how well it performs. This works well, but if your model is horribly bad, your users will complain. Not the best idea. A better option is to split your data into two sets, the training set and the test set. As these names imply, you train your model using the training set, and you test it using the test set. The error rate on new cases is called the generalization error, or out-of-sample error, and by evaluating your model on the test set, you get an estimate of this error. This value tells you how well your model will perform on instances it has never seen before. If the training error is low, i.e., your model makes few mistakes on the training set, but the generalization error is high, it means that your model is overfitting the training data. Data mismatch. In some cases, it's easy to get a large amount of data for training, but this data probably won't be perfectly representative of the data that will be used in production. For example, suppose you want to create a mobile app to take pictures of flowers and automatically determine their species. You can easily download millions of pictures of flowers on the web, but they won't be perfectly representative of the pictures that will actually be taken using the app on a mobile device. Perhaps you only have 10,000 representative pictures, i.e., actually taken with the app. In this case, the most important rule to remember is that the validation set and the test set must be as representative as possible of the data you expect to use in production, so they should be composed exclusively of representative pictures. You can shuffle them and put half in the validation set and half in the test set, making sure that no duplicates or near duplicates end up in both sets. But after training your model on the web pictures, if you observe that the performance of the model on the validation set is disappointing, you will not know whether this is because your model has overfit the training set, or whether this is just due to the mismatch between the web pictures and the mobile app pictures. One solution is to hold out some of the training pictures from the web in yet another set that Andrew Ng calls the train-dev set. After the model is trained on the training set, not on the train-dev set, you can evaluate it on the train-dev set. If it performs well, then the model is not overfitting the training set. If it performs poorly on the validation set, the problem must be coming from the data mismatch. You can try to tackle this problem by pre-processing the web images to make them look more like the pictures that will be taken by the mobile app, and then retraining the model. Conversely, if the model performs poorly on the train-dev set, then it must have overfit the training set, so you should try to simplify or regularize the model, get more training data, and clean up the training data. No free lunch theorem. A model is a simplified version of the observations. The simplifications are meant to discard the superfluous details that are unlikely to generalize to new instances. To decide what data to discard and what data to keep, you must make assumptions. For example, a linear model makes the assumption that the data is fundamentally linear and that the distance between the instances and the straight line is just noise, which can safely be ignored. In a famous 1996 paper, David Wolpert demonstrated that if you make absolutely no assumption about the data, then there is no reason to prefer one model over any other. This is called the no free lunch (NFL) theorem. For some datasets, the best model is a linear model, while for other datasets it is a neural network. There is no model that is a priori guaranteed to work better, hence the name of the theorem. The only way to know for sure which model is best is to evaluate them all. Since this is not possible, in practice you make some reasonable assumptions about the data and evaluate only a few reasonable models. For example, for simple tasks you may evaluate linear models with various levels of regularization, and for a complex problem you may evaluate various neural networks.